Oh. Oh.
Morning, Pat.
Good morning. Who was that
Richard.
speaking?
That was Joseph.
Oh, hi, Joseph. Hi. Good. We'll have Richard Berry here. How about that?
I've been pretty busy, but we've managed to find a executive director for AVSO.
Oh, fantastic.
So that has been a major time consumer.
Oh, I'll bet.
All the work involved is underground, completely invisible to the outside world.
Yeah, I'm sure. That's excellent.
So it's Brian Kloppenberg. Some of you may know him. He was involved in Epsilon Aurigae, a decade ago.
Okay. I'm sure Tom Smith probably knows him here, I would think. And we have Chile back. How was West Virginia?
It was amazing. It was so awesome. I had a wonderful time and did some really cool radio astronomy. So I'm very excited about it.
Cool. You guys started doing stuff in class on radio astronomy?
Yeah. A few of the things will make it into my curriculum. I'm sort of kind of figuring out how many and in what way. But yeah, it was really great.
That's very cool. That's right.
It was fantastic.
What sort of things would you have students working on in class?
Well, so we used the one of the telescopes, the 20-foot is robotic. And so I've done in the past, I've already do a thing on calculating the mass of the Milky Way from a rotation curve. Okay. Using the 21 centimeter line. That's already in there, but I might add something with the moon, because I led the moon project. The organizer of the workshop, Dan Reichert, kind of has this vibe where he tosses people into the deep end and tells them to lead projects. So he did that to me and told me to lead this moon project, which I initially had no idea how to do, and now I do know how, and it was really cool. So it was calculating the moon's angular size and thermal radiation was the idea. So that was really fun.
That is fun. That's cool. That's very cool. So and Sophia is free from.
I'm at Berkeley.
Yeah, you're in Berkeley, different background. Yeah.
Different background. This is the dorm room. And the schedule ended up working out that I'm here now. So hello.
Good to see you. So is Russ here?
Yeah, he's there.
Oh, he just walked
he's
away.
Not in his chair.
Oh, okay. I'm not I've got to look at those things differently here. Yeah, good. And got a couple. We got Joseph and Joel from our crew here, and Mark. And I know Mark has some things to tell us about what he's discovered with the test run we did at BARO. You want to go ahead and?
Yeah.
Mark, yeah, go ahead, because I want to hear what Russ has planned for the targeting, but he's not there yet. So.
Just need to enable, I think.
Oh yeah, I'm sorry. Yeah. Oh, there's Russ.
All right. Well, so let me know when you can see the Excel sheet.
We see it.
Okay. Well, out of the 10 targets in our first test run, that's the first automatic batch run. We've actually got 8 good measurements. Some like I rated as excellent. And they're good in that they have, decent.
Uh-oh, you froze.
Either extremely to the WDS catalogs, or in the one case,
Mark. Shoot.
I think our measurements
Mark,
is
Mark,
good on that.
you're freezing up. We're only getting little bits and pieces. You may
Oh,
need.
I'm sorry. We're having a torrential rainstorm here, and I'm using Starlink,
Oh,
and so it does cut out a bit. We literally went into torrential rain about a minute ago. But let me scan across to the actual is the catalog. And what you can see here, this is theta in these 2 green columns, the middle 2 of the greens. So for example, if I just choose one here, theta in WDS is 141.1, and next year projected to be 142, and we got 138. This is probably actually the worst one of all, but this is the one with questionable data. We actually get a 0.68 separation measurement versus 0.5. But when you look at the other ones, 338 angle, 337.6, 1.6, 1.521. Some of these ones down here, 343.8, we've got 343.7, 2.233 separation, 2.288.
Yeah.
So there's some extremely close ones to the WDS projections or actual measurements. And perhaps this one is the only one that's a significant way out.
which one's that?
This one is quite a faint star system. And if we look there again.
Okay.
Mark, does that one have an orbit predicted?
These are
Yes, it
orbits.
does. Actually, it's not that one. Bear with me a moment.
And is it a halfway decent orbit or is it a really preliminary orbit?
Yeah, that's exactly. These were, I think there was only one that was rated 2. The others were below that. He's frozen up here.
Pat, where'd the list come from and which telescope was it observed on?
This is BARO, and we're trying to find out how BARO works with automation.
Oh, great.
And it was it made up a target list because of our the difference in pointing between the 2 scopes. I made up a target list that is with only 1 RA across and 10 degrees of deck in size. So it was a small patch of the sky, so that when you did the initial centering on a target in that field, it was going to stay consistent throughout, so we could use a smaller ROI and reliably point. We found that when we point, because of the misalignment between the 2 scopes, when we point a wide separation in the sky, the pointing gets exaggerated, the error in the pointing, which means
Yeah.
it's a large ROI. So we were testing that, and it worked.
Yeah, you're getting great initial results, it looks like.
Yeah, we didn't really push the envelope on the separation, and I think that's, now that we know that we can actually do it, we want to really sort of push the envelope on separation. Because I think, Mark, what was the closest one that worked, would you say? Oh, he's still frozen. That's too bad. So that's a poor advertisement for the satellite system.
It looked like there was one at 6/10 of an arc second.
It was, yeah,
version,
6/10, yeah, 1 to 6/10 that came through. And so, we need to compare them to the orbital plots that we have to see how well it shakes out. But unfortunately, he's not working at all. So maybe we should just move on. Maybe the rainstorm will go away. Russ, you want to talk? You want to talk to us about the Chile targeting?
Yeah, so it won't take long. So the known binaries, we may have some data from August, but so far it doesn't look like we have much. But I've started a target list for the 2 telescopes for September, and we'll use the algorithm to set the exposure times this time, so we should get good results. And so Paul's lending a hand, Tom is lending a hand, and Sophia, if she isn't too busy, can help out. And we're going to try to get Nick and Leon to make sure they get on the observing program and get observed. Give us a hand on that. But I think we should get good results from that. The other thing that I'm working on, and I did send an email out this morning and that's the GDS follow-up. So I'm trying to set up a Zoom with our astronomer friend at the University at Paris Observatory, and get his help in doing kind of a preliminary target list so he can explain what we can do. And so I want to start with the speckle interferometry. But the other thing, and Pat, this is a question for you, maybe not September run, but maybe our October run, and maybe on BARO too. I'd like to do a little precision photometry of some of the DR3 eclipsing binaries. There's a whole bunch of new, and they're all short period. They're kind of 1 to 10 days.
1 to 10 days. You're kidding.
Yeah, these are eclipsing binaries.
Oh, okay. I was going to say eclipsing binary.
Yeah. And so what have you been using for precision photometry? I know I presume that what you're using on the exoplanet transits could be just used for eclipsing binaries too.
Yeah, that's what we use, and it's a nice backlit FLI CCD that's really good camera. It works very nicely.
And what software do you use for reduction?
Oh, we've been I'm trying to recall now. We did it all. We only did it one time, and it was all done in AIJ, which it was all done in AIJ.
Okay.
Yeah. And it worked fairly well. Joel on there has done a gob of exoplanet transits using AIJ. Do you have any other recommendation, Joel?
I mean, AIJ is probably the most user-friendly and easy to set up, unless you want to go over to some Python packages. Then yeah, I don't know. Typically what we've been doing for really precise transit observations is doing the differential photometry using AIJ, and then using another modeling software, mostly with Python code, to then fit the transit, because AIJ's modeling isn't so good, but its photometry is fine. So that's what we've been doing.
Yeah, and we'll need to use some different software for getting the minimum, the times of minima for the eclipsing binaries. They have folding software, and there's a number of different approaches.
Yeah, what's the open source one that everyone has adopted? I'm blanking. I keep on calling Phoenix, but it's not Phoenix. It's what's the name of it? What's that?
Phoebe.
Phoebe. Yeah, mental block there. Phoebe is probably the way to go. Yeah. Has anyone used Phoebe?
little teeny bit, not successfully. There's every summer there is a Phoebe workshop that one of these summers I will attend, and it seems like it does require that 2 weeks of immersion in the workshop in order to really master it. But I've done like little bits of stuff with it.
Okay.
Does Dirk Terrell actually do the workshops for you?
I don't remember the name. I think if you Google Phoebe workshop, it's like Andre something, I think. I don't know whoever it is.
Okay.
One of these summers.
Yeah, I have been talking to Bob Nelson
Yeah.
too up in Canada, and he's expert on this. We were going to try to meet up, but on Vancouver Island later this summer. I'm going to be at Bowen Island, and he observes up at Victoria, but he's come down with a serious case of cancer
Ooh,
and may not be able to make it.
ooh. I should not, I should mention the reason Scott's not here is his wife's not doing well with cancer right now. So
Oh, that's too bad, yeah.
it's a sad thing.
We're not getting any younger, Pat.
No, we're not. No, we're not. So, yeah, he's not been able to participate for the last week or two.
Well, that's all I have.
Okay.
I've got some preliminary results from
Oh, good.
from the CDK 24 in Chile, if
Oh, good.
anybody's interested.
Yeah, definitely.
Let me try and share my screen here. What I'm trying to do is to see if we can calibrate those telescopes for photometry.
Yeah.
You know, with extinction and transformation observations of standard photometric standard stars, the Landolt stars. So this doesn't have any conclusions except raises some issues. That's probably all we have so far. Nick's working on those as time permits, but it's a different kind of observing than what we've done with either exoplanets or with speckle. And so on the left side there, you can see the first plot. If I can get it to move over. Well, I can't, but this one, this is the instrumental magnitudes of a group of maybe 15 Landolt standard stars. And what I did was to take the plate solve images and just plate solve them and use Dave's extracted magnitudes as the data. So that's all this is, and those are a fairly consistent way of doing the photometry, and yet I think they're all probably different photometric apertures depending on how bright the stars are. So that's an issue. Anyway, this is plotted against air mass, and you can see that they're all at the same air mass, which is because we do the speckle data near the meridian. And these stars all happen to be near zero declination, except for a couple of them. And so they all have pretty much the same air mass, give or take a couple of, maybe a tenth, really small. So you really can't do any extinction measurements because there's no spread of air mass to look through. The second plot there in the middle is the difference between the magnitudes, the standard magnitude, Landolt's definition of the standard photometric system, the BVRI system, and what the instrument, what Dave's program, plate solve calculates. And the nice thing is that they're all really clustered closely together at the same magnitude. So that tells me, I think, that these stars are, well, that the telescope was, functioning properly, that the sky was reasonably good, and that the method of extracting the photometric data by integrating around a little circle is pretty good. They're all the stars are clustered here together, except for this one, which is very red star. And that's because probably the extinction is different in that red region than it is down here for most of these others, which are in the range of maybe a B minus V of 0.1 to or 0.2 to 0.5 or 6. They're all pretty close together. The last one, if I can, I don't know if you guys can see. Yeah, that's this same data of differences in magnitude between the standard and the instrumental versus color index. And that's the kind of plot eventually we'll use after it's all been extinction corrected for how much air it's looking through. We'll use that to say how much different is the instrumental camera filter telescope combination from the standard system, the standard Johnson-Cousins system. So you can see that this guy out here, the red one, is creating a variation because of its color, and that's the whole point. The redder, the more difference, the redder the stars, the bigger the correction, and that's exactly what we're looking for. There's a little bit of scatter in here for these others, and that's probably because they were looking through different amounts of air, slightly different, and they've been fudged by the atmosphere. They're not corrected at all. That's just this kind of spread. So it implies that there's really even a tighter correlation, because this has some extinction variation going on, and once that's corrected out, this should be even closer to a common linear relationship. Anyway, that's all promising stuff.
Oh.
I put down here the issues that need to be solved before this thing becomes practical. First of all, the goal would be to observe these in an ROI rather than a full frame plate solve. And I used 1 second integrations and changed the number of integrations to be depending on how bright the star was. That didn't work very well. Some of those stars are too faint for 1 second, and the signal is not really good even when you stack a bunch of them. So I'm going to have to increase the exposure time and make fewer integrations. I think the total time might go up by a factor of 2 or 3 maybe, but each individual exposure needs to be deeper. The speckle mode obviously allows only a narrow band near the meridian to be observed. So the telescope doesn't even go far off, because these are, it's working on speckled targets. And that's how I observed these, was because that's the only mode I was familiar with. But there needs to be a way to allow standard stars to be observed at a whole range of air masses, elevations, so that we can get a range of air mass to look through, and then you get a relationship of how much air is there and how much magnitude difference does that make. That's the first correction to make. And then you observe different color stars to see what the second order effect is on color. By observing those same stars through a bunch of different air masses. The other thing that's needed is that the ROI images are abbreviated in the FITS header. There's a really short FITS header, and it doesn't include air mass, whereas there's lots of information, including air mass, on the plate solve full frame images. So the air mass needs to be added into the FITS header for the photometry mode. Otherwise, it's a real hassle to try to figure out what the air mass was. You got to worry about time, and yeah, I've tried that before, and it's a nightmare. So I'd rather have a computer do that. I mean, the automated system that already knows where it's pointing and what time it is. And then lastly, the photometry mode, a different way of observing, really needs to be able to look at all the filters nearer in time. And plate solves are only done in the R filter because that's got the best signal to noise, and we can do the deepest images for the most number of stars to plate solve. So Nick and I have talked about these things already, and he'll work them as he has time. But anyway, I just wanted to take a quick look. And unfortunately, well, fortunately or unfortunately, that the night of the 8th of August was the first our first night on the both telescopes, and nobody else put in targets. So I got gobs of data, but nobody else got any. And then the next few nights when the double star or the binaries lists were up and Pat's list was up and everything, then it was cloudy. So, you know, catch 22.
Yep.
I think there's still a couple of more nights of that run to come, and I don't know whether it was cloudy or clear, but I think Leon will probably work on those and upload them whenever he has time. So that's all I have.
Yeah, I've been looking into this air mass problem, or issue. So I've added the air mass to the altitude calculation for the given star or the target. So then I can check which is the minimum and the maximum of amount of air mass, and then get one get the center as well. And then I have 3 kind of targets to get for every target, so I can calculate the place where I need to observe.
Oh,
So I've been working on it, but I didn't get it ready for last week.
well, it doesn't need to be a maximum and minimum and a middle. It can be random pretty much.
Oh, right. So how much difference?
Whatever's easiest.
How much difference do you need in the air mass? Is it like?
I'd say at least 2, probably 3 would be better, which is like about 15 degrees of elevation.
Okay. Yeah.
But
Yeah.
anything from 1 to 2 is useful. One from 1 to 3 is probably the goal.
Okay. And do you need like 3 times for every star, or?
Well,
or
more data the better, but no, not every star.
Okay.
There really is an emphasis on the redder stars, the bluer stars and the redder stars, because they have more weight, because they have a more extreme B-V color.
Okay.
Nick,
So,
what algorithm are you using to solve for your air mass below 30 degrees?
I think, let me just check, because I'm just using the one that Nina has got in it for now. That might not be correct.
yeah, there are several models, I suppose, and it, you know, since the air is not strictly a plane, it's a curved plane. It matters a little bit when you go looking through lots of air. I don't think it's going to matter a whole lot for air mass down to about 3, but if you were looking at 4, 5, 6, it would be way off.
So there's.
What do you think, Tom? Is 3 enough to cause trouble?
Yeah, it can. I mean, it'll sway your, you know, when you do land alts across the entire sky and elevations, it's enough to sway the values you get there. I would make sure that you use the correct algorithms for below 30, above 6, and, you know, and that kind of stuff.
Okay.
Right. So I think it's calculated using Guy Mard, 1993. Does it say anything?
Using what?
It's something like I'll just copy it into the.
Yeah, put in the chat.
The goal of this whole operation is well, number one, we can do, you know, photometric studies of variable stars or whatever targets with with improved accuracy of the photometry, once we have the system fully calibrated and transformed, and can take at least a few extinction observations through the night to make sure what the
Yeah.
extinction was, and eventually at such a good site as the Atacama Desert, we ought to be able to use estimated extinction and get really close. But for starters, it would be nice to take a bunch of data and just make sure that's good. And then
Yeah.
my ultimate goal is to try to apply those corrections directly to the bispectrum diffraction limited data we get for double stars, and be able to say specifically what are the color indices of those two components and derive their spectral types, which are not known for very many
That would be spectacular.
binary stars.
Yeah, that would be phenomenal.
Yeah.
That would
So
be
the
huge.
combination of a good orbit and those, a different kind of observation being the colors or the spectral types, those things together might really constrain the masses, which is really the goal. The masses of stars drive everything, right? So it can constrain them even more than the orbits alone or the spectroscopic data.
Yeah.
All a combination of different ways to look at it will improve things, I think.
Yeah.
And I guess these can't be resolved by spectroscopy directly. Some of them are double-lined binaries. So if you see signatures of both stars at once, you can tell a lot about them. And I think the ones in WDS that have two spectral types probably have been observed that way. But I don't know how close spectroscopes can resolve double stars. I don't know if there's any such thing as speckle spectroscopy. Maybe you know, Richard.
Maybe that's a new concept we should try and create, right?
Yeah, I think spectroscopy has always has the issue of the seeing disk to look at, and it really can only see one blob at a time.
Yeah.
It can't resolve to the diffraction limit like speckle processing can.
I think that might be something similar to what they do in some levels of chemistry to look at different elements in material structures. But yeah, let's ask Dave. I bet he would.
Yeah, he might know. I think the only way to resolve the diffraction limit is to use adaptive optics, with an artificial star and deformable mirrors and all that fancy stuff, which is available on a few big telescopes. But boy, you can't get time to look at double stars with those.
Well, I did see, was it Matt? He showed a video of them. They were installing one of these systems on the PlaneWave 1000. So I asked him when he was going to install one for us. It wasn't planned.
I guess there are tip tilt correctors available. I think SBIG used to build one. I don't know if there's better ones or newer ones out, but those kind of change the direction of pointing as the atmosphere moves the star around, but they really don't home in on the scattering of the light into a blob that destroys the diffraction limited image. So they improve things maybe by half or so.
Okay.
But speckle can improve things by a factor of, I don't know, 10. Resolution, I mean.
Yeah.
So are you gonna, the filter set that's on the 24 is the right one to use, the one on the?
No, well, no, it's just an imaging RGB filter set.
Okay.
It doesn't have photometric filters or Sloan filters, either one. So it's just,
it doesn't.
it's approximate. would expect not perfect matches, but reasonable matches.
Right, okay,
I mean, I think the RGB system for imaging should certainly be transformable to the standard photometric system, just that the corrections are a little larger and therefore they're probably a little less accurate.
okay. But the
Then if
1
we were
meter,
using-
the 1 meter would be better, right?
Yeah, well, the 1 meter is really the one I'd like to use because we can get to closer separation targets and it's got a real photometric set of Sloan filters, not the Johnson Cousins, but Sloan, which is sort of gradually becoming the more standard in the professional world.
Okay. Okay, so are you planning on doing that or?
Yeah,
Yeah.
there was some data on the 1 meter this time, but I had 2 programs and I got a gob of data for one, but not so much for that photometry trial.
Okay,
On the 24, that was the only program, so I got a lot of data. So that's why I analyzed that one first. Now that I know that answer, I'm not going to bother with the 1 meter data because it's really sparse and not too useful yet.
okay, okay.
Rick, it'd be interesting for you to compare some of the Landauls you do, extinction coefficients for those compared to the APAS values, that you use.
Right.
I'd like to see
Yeah.
that. Yeah.
Yeah, we'll have to do that because they should be very similar.
Yeah.
They both, well, now the Chile telescopes have the BARO Sloan filter version, and APAS used the Astrodon set, right? So they're going to be slightly different, but they shouldn't be very much different, except for maybe Z. It's always a problem child.
You might have a linear offset, but it'd be the same.
Yeah. Yeah, the slopes should be the same.
Yeah.
I think the filter widths are probably the same.
Okay.
But anyway, Z is always an issue because the cameras are running out of quantum efficiency and that they're all, I think all the wannabe Sloan filters are really slightly different than the one that was on the original system and the one that Arnie used to be the truth model that the whole big Sloan operation used as correct. Arnie's photometry was, everybody knew it was better than anything any automated telescope could do. So he became the truth model. And unfortunately, the filters were different between the two because Arnie's were exposed to air and the Sloans were exposed to a vacuum on one side. I mean, the big Sloan telescope itself.
Right.
So, and that made some subtle difference in the responses. So there's even a correction within the Sloan overall operation.
That's
crazy.
That's very.
Richard, what have you been up to? Long time no see.
Well, as I said earlier, the search for a new executive director of AVSO was an incredible sink for time, and we're still trying to get ourselves reestablished in a new place. But what I'm working on now is working with a bunch of educators, including Don Bruns, who did the Eddington experiment last year at high precision, and my small group with Toby Dittrich, who did the experiment and got a fairly accurate but large error bar result, probably largely due to a lot of atmospheric turbulence at low altitude. But we're going to do this again in 2024. We have a site in the mountains in Mexico at 8,000 feet, and we're going to try to do what Don Bruns had done with the NP 101 optics and you know, a medium-sized sensor. We're also going to be trying with a much larger sensor to see if we can get away from this business of having to look at alternate fields. So we will have at least 4 stations. We currently have 4 NP101 sitting in my workshop. Toby Dittrich's great power is that he can write grants and get money. He's really good at this. So we have a fair amount of equipment to do this with. It's education oriented. The idea is that yes, as Kelly says, it's a useful skill to be able to, and he writes terrible grants and they still get money. So who knows? Grammar checking is not important in writing a good grant, it turns out. But at any rate, so most of the people involved are physics teachers, so they don't know much about astronomy, and that's sort of why I'm involved. They want somebody to help teach the physics people how to run a telescope. But the purpose is to develop a complete pipeline of telescope control software based on Python, and then reduction software that will be based on Python. This will then be available to anyone who wants to do the experiment. Toby thinks we may have as many as 24 different groups, not all at the same location, but all over the US. You know, physics teachers who decide to give their students a project that is, you know, short term, not too difficult to do, and you know, a real result. Part of the reason for wanting a pipeline so that reduction could be done, complete data reduction could be done within 2 or 3 days afterward, is that by experience, we've learned that students lose interest if it takes 6 months to reduce the data. Somehow, you know, their lives continue, and the data just sits there. So we have a physicist, 2 students, maybe 3 students, who will be writing the bulk of this software. She's paid for with a grant. Heather Hill is the name. She's local. She and the students have been up to my place, and we're shaking down the equipment. But the reason I wanted to talk to this group is basically not this time particularly, but to have a group of people who I can talk about astrometry with, because the whole purpose is precision astrometry over fairly wide fields. So that's, you know, that's why I'm here, the proximate reason. And I will probably be, you know, trying to pick your brains for that. I've got a couple of emails out to Dave saying, Dave, your software is really wonderful. It's one of the few things that can actually happily do a nice plate solve on 64 megapixel images and do it reliably. And the problem is, well, how do I get the raw data out so that we can flow it into our software and use it? When you start to develop software for, you know, student laptops, all of a sudden trying to handle as many as 100 61 megapixel images at a time is not necessarily a going concern. So we're looking at solutions like, we know where the stars are going to be in these images. We do a quick plate solve, and then we take little boxes, little 64 pixel boxes for each of the 200 stars we might have detected, say for 100 images. Now you have a very tractable amount of data, and you can develop routines that are very specialized for getting good photo centers out of very, very noisy data, because you're looking at the corona light, you're looking at turbulence, and you're looking at short exposures in the order of a second. So there's a bunch of challenges here which are kind of interesting. I will try to engage with Dave. I do have one question, and this may be just my stupidity. How do you get the raw data out of Dave's program? You have that little thing called test, and it's got the data that I would really like to use as sort of feedstock for analysis, for doing things like, just squaring on the optics. Is there a function in his program which will dump that file? Because you can't.
It'll dump the all the data it extracts from the plate solve into a CSV file, if that would help.
Yeah, that's what I want.
Yeah,
Well, it already does that.
yeah, it does that.
Where is that? Which function is it?
I think there's a button on the bottom that says, I forget what it says, but there's a
Precision astrometry. Is that what-
no, well, no, just
You want to share your
Take a look.
screen and show?
Yeah, I mean, this is a stupid question because what I would normally do with a window like that is just like select all, copy, and paste it into a text file. And
yeah, that's it already does that, I think.
Yep.
you can't select it. No.
His,
Or at least
his
you can't
older version did, Rick, but I think he took it out, didn't he?
Really?
I don't know. Took it out for what? For the automation or?
I don't know why he did. I thought that there was a
Well-
discussion that he took that out before.
Well,
I've been using the 3.79 version, which is a little more hands-on. And can I
have
Go ahead and share.
3.78 right now.
Okay, I think the 379 uses the Gaia database. So it can go quite a bit deeper, down to, I don't know, 18th or something like that.
Okay, well, knowing that it's possible to do it is half the battle. If I know it can be done, because this is this kind of thing where you go like, where is the function? Where did he hide it? But I mean, my naive thing is like select them all, paste it into a text file, and then parse that text file. And I know in Visual Studio, it's a very simple thing. You just have to select that text file and make it a selectable text file. That's just one of the parameters of the text box.
Let me share my screen, and maybe it's
Sure.
I think it should be
Go
easy
ahead.
if I could figure out how to share my screen. I always have trouble with this.
It's the green
Yeah.
button on the bottom, and then you have to figure out how to okay, there we go.
Okay. You see it?
Right, got it.
Let me just open an image. Yeah. Kind of
Got
at
an image
random.
open,
Yeah, but let me
and it's been plate solved.
do the whole thing. Okay, I'm opening a new image. It comes up with a kind of a zoomed in version. So I hit the expand, and I like to brighten so you can actually see the background.
Yeah.
And then you do the plate solve, which is this little, do you see the plate solve?
Yeah, I'm familiar with that part.
Okay.
Yeah.
Okay.
Okay, it's working on it.
And
Now all it
bingo.
is this button to the left. It says show
Right.
extracted.
Right, now you get a window that's called test.
No,
Okay.
just show extracted. Do you see that?
Oh, show extracted. Okay.
And that's a sort of a text file. And down in the lower left, it says send text to clipboard.
Oh, okay.
and it puts out a CSV,
Great,
which you can then save anywhere you want.
great. Okay, that's the,
And those things on the header show what kind of data it is. Is that all you need, or you need something else? Sequence number, which you don't really care about, but the X and Y
signal noise
centroid,
ratio,
the total
RMS.
integrated in the aperture, whatever aperture he's using, but he doesn't say what the size is. So maybe that's something useful.
Yeah, he
Signal
has some
noise.
kind of adaptable thing.
Yeah, it fits the aperture to the brightness, I think. And signal noise, RMS, I'm not sure what RMS that is. Aspect ratio of the image, is it nearly circular for
round?
one, or
Yeah,
is it oblong? The magnitude estimate, the UCAC4 version of that star magnitude, and then the RAN deck that it's calculated.
Great.
If that's everything you need,
That's
then you're
more,
ready to
that's,
go.
yeah. Now, if you click on the test button, you get the same file, right?
I think test was something Dave played with to see if it was working right or something. I don't know.
Okay, okay.
I've never gotten anything useful out of that.
Well, it duplicates this data. And that's what I was trying to find. I was trying to get my mitts on.
Okay, well, that's
Pretty much
easy.
answers my initial question.
Good. And you can set, when you do your plate solve, I think you can set the parameters. So you might want to go very faint to low signal to noise and see if you can find fainter stars that are noisy. I don't know if whether you'll have to play with that.
Yeah, I mean, that is, I mean, we know where the field is, okay? So all we have to do is what you'll find is that, and the field behind the sun is not particularly good. It doesn't have many bright stars on it. So we're looking for like 8th and 9th magnitude stars that will be hard to find in the images. But once you find 3 of them, then you know where all the rest of them are. Okay, as soon as you can do a 3-star plate solve, you can make your little boxes, and then you got to clean up, you know, all the garbage and get down and find out where the stars are hanging out.
What sort of field of view are you going to use?
It's 3.7 by 2.4 with this is much bigger.
Degrees, huh?
Degrees, yeah.
I hope
with
there's not a
with
limitation
small-
on how many stars it can solve.
Well, no,
I
there's
think-
no problem.
I think there is a parameter that he sets.
Oh, that's not the issue. I mean, we're talking about, you know, if we can get a 10th and 11th magnitude stars around the eclipse, we're doing super good.
Yeah.
So it's the problem of a very, very high sky background,
Right.
say 2/3 of the way up full well, with a 9th magnitude star and a short exposure.
Yeah.
So, I mean, we're hoping to get signal noise ratios like 20 for stars that we can then get a good centroid for. And part of the reason we're going for the higher altitude is that the scintillation and turbulence is very significant. The stars in my images at 200 meters elevation, we're dancing around by 1 or 2 arc seconds from between one exposure and the next. You're trying to get 20th of an arc second stuff. Don Bruns at 6,000 feet had much more stable seeing, but less clear skies. We had very clear skies, but lots of turbulence. You know, it's astronomy, right? You pay your money and get your choice. Well, I will let you guys know, you know, regularly what we're getting and what we're seeing. It's a very different kind of thing than what you're doing, but it's all astrometry.
Dave has an interesting little spreadsheet for signal to noise estimation that might be useful, but you probably already have
I've used
stuff like
that.
that.
Yeah.
Great. Yeah, keep us posted on that. That's very interesting.
These finding images, our test thing is shooting images of the full moon, and seeing what we can see around it. And there's a lot of funny questions. We've assumed that a red filter, a Sloan-R prime filters, is the right filter to get highest signal noise ratio. But, that seems like the sky should be blue, but, would we be better in a different passband?
You might try an eye filter, just because the seeing might be a lot better.
The seeing may be better, but the optics may be worse. Again, the NP101 is not really designed for. In fact, the R filter, the images show significant chromatic spherical aberration. So you're taking the NP101 and stopping it down to 80 or 75 millimeters to get really crispy stars.
Have you tried the Y, Sloan Y?
We have not, no. We're pretty early on in this whole thing. What we want to do is this year lay the groundwork, do a lot of experimenting next summer. And I say summer in part because it's the only time of year I have clear skies. Right? It's Oregon, right? Rains all winter. But we will have people all over the US hopefully involved in this. And we'll sort of be, I think, trying to work as sort of data central for them. And sending out code and saying, okay, can you guys reduce their data? What are you getting? Trying to do astrometry of faint stars around the full moon.
Did you get involved with the Citizens Cape project last go around?
I did not actually. I had a whole series of conversations with Matt Penn.
Yeah.
But then I got involved in the Dietrich Bruns collaboration.
Okay.
And that was a very different thing.
Yeah. Do you know if they're going to do another Kate this go around?
I don't know.
Yeah. Matt had his hands full doing that. That was a big project. We had a team in Oregon, not far from your place.
Yeah, that would have been Mike Conley.
Yeah. Well,
yeah.
No, yeah. Mike was running the Oregon. Yeah. But
we're
at Madras.
Yeah. Well, I was the guy who introduced Mike to Matt and said, okay, Mike is the guy who can do this. He's doing a lot of stuff and he's still using that telescope to take images. He's having a lot of fun with it.
One of our students is still using it. Yeah. I've got the computer from it behind me, but it was not. It's on its last legs. Anyway, that sounds interesting. That's a long range project. We want to see what we can do. It'd be fun to work with that. Any other stuff? I wonder if Mark has a better connection if the storm blew by. If so, he might be able to show us a little bit more about that. Is your connection better?
Yes, it is much better now. So
okay.
Yeah.
Okay.
Apologies for earlier. So I'll turn my video off just to save bandwidth, but let's show you that list again.
I'm particularly interested in the closest one you've got and see what.
Yeah.
See what the magnitudes are and so forth. Maybe you can highlight that row and sort of go across it and see what it looks like.
Yeah, so you can see the Excel spreadsheet okay?
Yeah.
Great. So, so many of these separations we're down to as little as 0.4 for the row figure. We're getting on that particular one, we actually got 0.619, so that one was somewhat of a difference. But we just about managed to get down to 0.4, 0.5, okay, as far as what the theoretical or previous measurements were. Our measurements tend to be a bit larger on those. This one here has a significant theta variation. Actually, this is arguably on the face of it, our worst set of data, because you look down here, we have, great alignment with, theta 343.7, we're at 3.3.8, 165.6, 166.3. And on the separation, 1.577, 1.528, 2.288. So those are all good. That as you go down to the smaller separations, we seem to have more difference in our results.
We'll need to look at the plots on those because I'm seeing things and how.
This one, the plot is really, to me, is really suspect. So this is the one I wanted to show you. So I'll stop my share on the previous document and start it on this plot. And when you look at this plot, well, look, there's
there you go.
there was nothing on here, right?
Right. Okay.
So
yeah,
so
the
just
orbit's obviously wrong, so I wouldn't.
Yeah, exactly.
not-
So
not
not
matching it.
bothered about that one.
Yeah.
All right, that one's terrible. So let's go back to the spreadsheet again. Let me stop my share.
I think that's one of the takeaways from this experiment was the let's look at the plot before we put it into the target list, because some of those will never be able to to prove anything with something like that.
Exactly. And the other one that has a certain amount of difference that stands out is this row here, 0.5, we get 0.68. The angle's a little bit out. But it's not too bad.
Depending on the period, that may be okay. But
Now
let's look at the plot on that one.
Yeah, let's see
let's
it
look at
match
the plot. Yeah.
an orbit of a good match.
Yeah. That's a grade 4 orbit, so it's not going to be too good.
No, and it's definitely not too good. So I'm going to share that one. Yeah, again, I mean, there's a lot of historical measurements, but look, there's not a great deal. Now let's remind us as to what the numbers were on that one. So we had our theta was measured at 345. The plot projection apparently is about 275. But we're down here.
That must be, boy, when was that's interesting. That's interesting, isn't it?
Yeah, because the last measurement, well, there was apparently a measurement on 2016, but I can't see where that would be given. Well, the period is, at 100 years. So I mean, it's
almost looks like you're 180 degrees out.
Yeah, it looks like it's 180. That's what I'd guess. I think 180 out. Yeah.
Yeah.
I think we are. And then that starts making sense. Yeah.
Let's have a look at that then. Yeah.
Yeah.
So we we measured 221 at 180 degrees. I'll pull up the image for that one.
Yeah.
So this is
so that's 41. Yeah, that'd be just about right. That looks about
18,437,3141.
So that would be just under 45 degrees. And it was at 0.6, which, yeah, that's believable. Okay.
And this was probably actually one of the hardest images to analyze as well.
Okay.
Let's have a look. So let me share the screen. This is definitely, I think, one of the hardest images.
Is that one
So
of our redder stars? Is that the reason? I mean, we talked about that the other day, Rick Wasson and I were talking about it. And as you,
interesting.
yeah, you know, you might be selecting the incorrect reference
Yeah.
versus the target.
Right.
So we're on, yeah, 3141, that's correct. It's well, it's a K0 star, so at least the primary is.
Wow. Okay. So what was his magnitude? Do you recall?
So its magnitude is at the extreme. So 9.71 for primary, 10.29 for secondary.
Yeah. All right. Well, that's not too bad. And,
Yeah.
and what sort of exposure was that run at? Was that
So this was at 40 milliseconds.
40 milliseconds? Okay.
Yeah.
Okay. Yeah, we didn't have the benefit of Leon's calculator for determining the right exposure times. Which reminds me, Nick, has anything happened on the focusing? When you is it George that you were dealing with?
Yeah, he hasn't had time yet to analyze the data yet. So I'll ask him again, but I know he's really busy.
Yeah.
So it's
Understood. Okay, I
yeah.
just if he needs more data, let me know. That was
No, you had quite a lot already in there, so I'll ask him to if he's got time to look at it.
okay.
Mark, one more comment. Looks like your apertures are overlapping and you're going to get contamination that way too, if this is accurate.
Yeah, it's, as I said, it was a really hard one to do because you couldn't, to get to a stable position, the only way you could do it was to overlap them. And I tried changing the apertures up and down. We're really, I think around 0.4 arc second separation or even 0.5. I think we're around to the limit, certainly within the parameters we've used here. You know, I think you have to have a particularly good image because there is some overlap. What I've tried out a few times as well is not going down to the minimum error and actually taking a slightly more, basically a more distant view, because what tends to happen is you see more, even though the error's reduced, you tend to see more saturation around the image. And one of the other big points here, by the way, which I wanted to mention today from this first phase, is for these shorter separation images, if we change the number of pixels to being 256 by 256 instead of the 512, it greatly improves the ability to do the astrometry analysis. This is one, for example, when I look in the 512 image, and let me just pull that one up, and you'll see that actually it just looks like a bar that is not useful to do anything with.
Now, was this okay?
Yeah, so let me show you that, because it's really illustrative of the fact that when we go down to shorter separations, I think we have to revert to 256 by 256 pixels. And I was going to ask Rick, is there trying to, you know, it almost seems counterintuitive, right? Because if you have high resolution, you'd think you'd get a better image, but maybe you don't at the shorter separations. I don't know if you've got any comments on that.
I think I usually use smaller ROIs, well, 256 to take the data and sometimes 128 to analyze it. But Dave's comment the other day, or I guess he said it several times, he thinks that there's an increased possibility of aliases when you shrink the ROI from what you originally used to take the image. So he prefers to leave them at 512 or whatever you use to take the original images, and then just zoom in, you know, till you can see some pixelation, and then you're kind of at your limit.
Sure.
I think you might play more with the high and low pass filters and improve the
Ah,
separation a little bit there.
okay. I see. Because when I just take the 512, right, this is what I get. I just get an oval shape.
Yeah, but zoom in on it and then reduce the brightness a little bit
Okay.
and play with the long pass filter, and you should start to see less fuzziness, I hope.
Okay,
And shrink the size of the apertures. You don't need to.
Yeah.
You don't necessarily need to get all the light to do the
Right.
astrometry.
Yeah, no, those are great suggestions, Rick. Okay, well, I'll try reprocessing with that in mind.
It's a
Different
definite
filters.
challenge because you're
Yeah.
right down there at the Rayleigh limit, you know.
Yeah.
I think the Rayleigh separation where you sort of putting the secondary on the minimum of the first ring is 0.38 or thereabouts. So you're right there already.
Right. Yeah.
Not gonna do too much better than that.
oh, yeah.
Right. Gotcha.
Right,
Yeah, because I mean, some of the other images were truly amazing. In fact, although it didn't get rid of some of the duplicate artifacts, if I can show you guys one more that I think would be very interesting to the group. Let me pull that one up. Bear with me a moment.
which one are you pulling up?
So I'm going to pull up the 1843 3940, and this was with 512 by 512 pixels, and let me show you this one. So and this one you get 4 dots. There's actually 2 double stars in here, so the primary with 2 secondaries, so 2 different measurements made. There's this extra one down here, but they both came out with truly excellent results. I mean, this was fantastic. I mean, for example, the one of the pairs, let's see, so this is 1843 3940. There's an AB and a CD pair in here. That's what they're called, at least in the naming convention. And we got 73.09 versus 72.9 on one of the position angles, 343.8 versus 343.4. And on separations, 2.398 versus 2.405, 2.233 versus 2.288. I mean, great correlation, really worked well. And of course, these are decent brightness. They're all around, magnitudes 5 to 6.
Yeah, these are really bright. Yeah.
And obviously wide separation too. I mean, I could make the images even bigger here, right? It would still be good. So I could zoom in even more, but to get even better results. But so there were some really good ones. And overall, yeah, apart from where you hit near that 0.4, and as you say, a 0.389 kind of will be the best case scenario entirely. We still get some decent images. And I think with some more practice with optimization, as you suggested, Rick, I think we can get to that point. We just really obviously can't go lower than that point on this particular, on this scope.
Right.
But of course, on the larger scopes in Chile, we could still obviously push that lower. But pretty good.
Yeah.
Yeah, that's great.
Yeah. Okay.
I've never seen a quadruple like that. That's beautiful.
No, yeah, I know. And it was, yeah, and I'm sure, like I said, I'm sure I can tweak it even more with some different filtering, but yeah, it came out superbly though. I mean, it really did. So these are the 2 that are both about 5, and then that one there, I think, is the 6th one.
Mark, let's plan on doing another observation run tonight or tomorrow night.
All right, I'll hand it back over.
And let's apply Leon's new model to figure out our exposures and some of the other lessons learned so far, and see what happens with that.
Yeah.
Okay. Are you free one of the nights? Are you free tonight or tomorrow night?
Yes, yes, I can be.
Okay.
Yeah, let me
All
know.
right. We can check that out.
One thing I'd suggest for those really close ones, if you have, you're not limited by telescope time on BARO generally.
Right.
Right.
But make 2 or 3 or 4 sets of observations independently, and then see how they compare.
Right.
And you can get some statistics on the astrometry.
Are you thinking about multiple nights? Or are you thinking about
No,
one
yeah,
night?
same night
Same
would
night.
be all right.
Okay.
Yeah.
Okay.
Yeah.
Yeah.
Okay.
We were just doing single runs, but I would definitely like to do that.
Separate nights might be better, but
And we're using 500 instead of 1,000. Should we up it to 1,000? Do you think with that images?
What was your signal and noise?
that would, yeah, for the fainter ones, what are you using? 500 exposure?
500, yeah.
That should be enough,
Should be enough. Okay.
especially for these bright stars. Yeah, you got pretty good signal and noise.
Okay. But what
Another interesting test might be to use the different apertures as well, the 512, the 256, and then on the same set, and then you could take a look at the difference on those.
Yeah, there shouldn't be any difference, I don't think, but maybe I'd be surprised.
Okay.
Wouldn't be the first time.
Yeah. That would be worth it. Yeah. We'll definitely
No.
shot.
Great. Thanks for the suggestions there, Rick.
Yeah. All right. Well, we'll set it up tonight. We could.
What sort of exposures did you use on that bright one, the 4 stars?
Let me just check.
You could probably get away with maybe 10 milliseconds.
Yeah, it might be able to-
Yeah, it was actually 20 milliseconds
Okay,
on
right.
that.
Yeah,
We just had no basis for, we was a guesstimate, at this point. So, yeah. So, yeah, we'll learn from this and see if we can improve our exposure times.
well, the goal of the shortness of exposures is to freeze the seeing. And once you've done that, you might as well keep it as long as reasonable in order to get better signal and noise. So there's really no reason to go shorter unless you're starting to saturate.
Right.
Yeah.
But 40 milliseconds on those 9th or 10th ones is usually pretty good. And in my experience, you get enough signal.
Okay.
And if you go very much longer than 40 in red, you start to get a little smearing.
And we're doing these in eye.
Oh, well, and now it's easy to go to 60 and you can even go to 80 in eye, I think.
Right.
Yeah. There's something squirrely about our Sloan R, and I don't know. I'm going out there Sunday. I'm going to find out if there's something. I'm going to take a good look at that filter.
Hmm.
Yeah. And we're going to put in Star Lake so we can, but fortunately, you don't get rainstorms like you do in Atlanta.
Oh, shit. I tell you, I wish I could pump some of this water your way. It's just crazy right here.
The eye filter limits your resolution a little bit more because the airy discs are bigger and you can't look at things quite so close together.
Okay. Yeah, I definitely want to be able to get the R filter working right. We've already had to replace it once, and I'm annoyed that it's, I put a new chroma in there and it doesn't look right. So, don't know what to make of that. Okay, anything else? We covered it for today. It's pretty broad discussion today. I liked it. It's fun. A lot going on. So we'll go ahead and we'll plan on next week, and maybe there'll be some more stuff. Hopefully we'll have some more from our end, and maybe there'll be some of the Chile data be available too. Okay. See you next week.
Okay.
Yeah.
Thanks for coming, Richard.
Bye for now, everyone.
Bye.